we don't know if you have made an error, we can at least understand what the potential errors are, and we can choose which error that we want to minimize the risk of. So we have a little bit of control as to how likely it is that we make one of these two errors. So in order to do that, you need to be able to identify what the type 1 and type 2 errors are in context and decide which one is worse. You can't minimize both unless you take a larger sample. And if we can't do that, then you just have to pick one error to minimize, and then the other error ends up being increased some because of that. So in example 10.6, if we're looking at the U.S. Department of Transportation report in 2015, that 79.9% of all domestic passenger flights arrived within 15 minutes of the scheduled arrival time. So if there was an airline with poor on-time record, decides to offer employees a bonus if the airline's proportion of on-time flights exceeds the overall industry rate. So here, P is going to be the actual proportion of the airline's flights that are on time during the month of interest. They take a sample of flights to see how they're doing. So your hypotheses, the null is that they simply meet the domestic travel overall rate, 0.799. But what we're interested in is that they've exceeded that, because they get a bonus if they exceed it. So did they meet it or did they exceed it? Now, you might start thinking, what about less than? That's possible too. Well, that's actually built into that entire null hypothesis, where if it's something less than, that's still going to end up in the null. I know that's a little shaky right now, but the way that the math is happening behind the scenes, you do have that less than would still be not what the company's looking for, so the company's really not interested if it's less than. They're only interested if they've exceeded. So what would our type 1 error be? Well, this is where you would reject the null, going for the alternative, but the alternative was false. So I always start with thinking about what you conclude. So here you are rejecting a true null. So basically you conclude that the proportion is greater than 0.799 when it's not. So what are the consequences of that? So you give everybody a bonus, but they really didn't deserve it. So it looked like they were on time, but they really weren't, so they shouldn't have gotten that bonus. Now, I will take a moment to note that it probably wouldn't be that hard for this company to look at all of the on-flight data, but we're not going to worry about that actual context here. With the world of computers, I think we could probably do better than just taking a sample, but we're not going to worry about that little small detail for this exercise. Now, what is a type 2 error? Well, this is where you fail to reject a false null. So fail to reject a false null. Okay, you've made a mistake. You didn't get rid of a null when you should have. It was wrong. So here we would conclude that the proportion was 0.799 or less, when really it was higher. So here you conclude that the proportion was in fact 0.799 when it was actually higher. So what happened here? Your employees deserved a bonus that they didn't get. So which one in this case is worse? Well, you'd have to really think about who the interested party is here. If you were the employees, then you probably would think a type 2 error was worse. If you're the management, it could probably go either way. But in a real world scenario, you'd have to decide which one are you more willing to make versus which one are you less willing to make, and you'll do something to minimize that. And I'll tell you what you do to minimize that here in just a few minutes. We look at example 10.7, we look at this new heart stent used to treat arteries blocked by heart disease. So this new stent, the Libert, maybe, I'm not sure how you pronounce it, is made of thinner metal than the current stents. And apparently I don't know how to spell stent because I have an INT and an ENT. One of those is right and one of those is wrong. So the problem that can occur if the artery becomes blocked again, that would be a bad thing. So the FDA is going to require this company to provide evidence that the proportion of patients receiving the Libert stent who experienced a reblocked artery was less than 0.1. And that's based on the current Express stent reblock of 0.07. So basically the FDA is saying, hey, we're not going to approve this alternative unless you can prove that it is no worse than what we have right now. They give them a little wiggle room here, let it go up to 0.1, but that's not a huge difference. If this stent was not effective with preventing reblocks, then it's not going to get approved. So we need to think about our hypotheses here, and the first one is that it's equal to 0.1. Okay, so that's what the FDA is stating, like if you meet this, you're okay. And what we are, if it's 0.10 or greater, the FDA is going to have a problem with it. What we want to see is that it's actually less than that. So what would our type 1 and type 2 errors be? And I'm going to put this one into a chart so that you can kind of see what's going on in a little bit different of a way. Remember, a type 1 error is where you reject a true null. So here, in context, that's where you conclude that the reblock rate is less than 10% when it's really not. So here, what are the consequences? Well, the stent is approved because the FDA said that you've got to have less than 0.1, and we concluded based on that sample that it was. That just happened to be a sample without a big reblock rate. So the stent gets approved, but the reblock rate is higher than the old version. Then our type 2 error is that we fail to reject a false null. So we conclude that the reblock rate is not less than 10 when it really was. So what are the consequences of that? Well, the stent is not approved, but it should have been. And I'm certainly looking at a relatively simple version of what goes on behind the scenes. Don't think that clinical trials are this simple. They're not. But we're just starting our study of statistical inference. And this is one aspect of what goes into the bigger picture. Now, we also hope that we don't make one of these two errors, okay? Most hypothesis tests don't end up in an error, okay? Most of the time we get it right. But we just need to be aware that there's a possibility that our sample does lead to an error. And so we just have to be able to consider which error would be worse to make, and then just try to set up our method in a way that doesn't lead to that error very frequently. So which one of these errors do you think would be worse? Well, I don't want to see something on the market that is less effective than what's already there. So for most people, this would be the worst case. The type 2 error just means that a lot of money and research and time went into this stent that should have been approved. But that's not necessarily that bad of a thing, because you could always run another test and submit it again and show that this was just, a bad sample and do it again. Might cost a little more money, but it would be a lot worse if you approved something that wasn't as effective. So I've mentioned a few times that you can limit how much error that you make. And so we're going to first define these. The probability of type 2 error is alpha, and you can specify that. You can define what the probability is of making a type 1 error. Type 2 error, you can't directly control that one, but we state that as beta. If you take a second statistics course, you'll learn how to calculate that beta. We don't do that in this class. But even though you can't directly control, if you need to lower your beta, then you just go with a higher alpha. And so what you determine is which consequence is worse, okay, type 1 or type 2 error. And so what you do is you define the largest probability of a type 1 error that is acceptable. You carry out that hypothesis test using this maximum acceptable value as the significance level. That's basically the level where you decide whether it's a likely or an unlikely observation from that null distribution. So if you pick a smaller alpha, then you're going to have a larger beta. If you pick a larger alpha, you'll have a smaller beta. So that's the only way that you can control the probability of these type 2 errors. And so in this case, in example 10.7, we needed to minimize the type 1 error. And so we want to have the smallest alpha. And so here, typically your alpha values are 0.1, 0.05, and 0.01. If you're trying to minimize a type 1 error, then typically you would pick the smallest value of alpha, 0.01, and that would be your cutoff for determining if something was likely or unlikely.